Okay, the next thing that we're going to talk about is Pascal's principle. Pascal's principle states that if you apply pressure to a fluid that's enclosed, which means that it's completely fills up its container, then the applied pressure is transmitted undiminished to every point in the fluid and to the walls of the container. So let me just explain this. So suppose you have a container which is completely filled with fluid. So there is no air bubbles. So you've completely filled this up with fluid. And let's just say that there is a little piston arrangement over here. You can move this piston up or down as you wish. All right, so right now you're not exerting any pressure on the piston, and this entire container is filled with fluid, right? Consider a little fish over here, and let's just say our fluid is water. What is the pressure that this fish is feeling? So the fish is at a depth h, so the pressure that he's feeling is going to be h rho g. All right. Now let's say you start pushing down on the piston now, right? Let's say that the area of the piston is A, and the force that you're applying is F. So how much pressure are you applying through the piston? The answer is, let's call that P extra. The extra pressure is just F divided by A, right? So once you start pushing down on the piston, how much pressure is the fish going to feel? Well, according to Pascal, the fish will immediately feel that extra pressure. That extra pressure will be transmitted to every point in the fluid. So our little fish will start feeling H rho g plus P extra. If there's another fish over here, same thing. Prior to you applying the pressure, he would only feel the pressure of H rho g, which is just the pressure due to the depth. But once you start applying the extra pressure, he's going to feel H rho g plus extra. So the extra pressure is transmitted to every point in the fluid and also to the walls of the container. The walls of the container will also feel the extra pressure. Okay. So what Pascal's principle is telling us about fluids is that fluids are essentially incompressible. Why? Because if you're applying pressure to one point in the fluid and the entire pressure is being transmitted to every other point in the fluid, what that means is that the fluid is not able to make room, squeeze and make room, right? And so the entire pressure that you're applying is being transmitted to every point in the fluid. This would not have happened if instead of the fluid, you had a gas inside the container. So if you apply pressure to one point in a gas, then the gas can easily compress, and so other points in the gas would not necessarily feel the same pressure. Since this does not happen in a fluid, what you can conclude from here is that a fluid is incompressible. All right, now let's consider this example. Suppose you have a can, a soda can maybe, which is completely filled with water. So it's completely filled with water. Draw it like this. And suppose you have another soda can that's not completely filled with water, but half filled with water. All right. Now suppose you fire a bullet into both of them. What's going to happen to the soda can that's completely filled with water? Well, let's think about it. When the bullet strikes the wall of the can, it's coming in with a tremendously high velocity. So the force that it's applying is enormous. So enormous force divided by very small area over which the force is acting, and that's just the cross section of the bullet. So very large force divided by very tiny area will give you a very large pressure, right? And that very large pressure is now going to be almost instantaneously transmitted to every point in the fluid, because the container is completely filled with fluid. The fluid is fully enclosed inside the container. The container is full of the fluid. There's no air bubble or anything. So that entire pressure is going to be transmitted to every point of the fluid and the walls of the container. So then what's going to happen is that whichever is the weakest wall is going to give way. For a soda can, it's the top part of the can is the weakest, and so that's going to give way, and you're going to have an explosion of water rising up from the top of the soda can. What would happen if you fire a bullet into this can? So again, there will be an enormous amount of pressure applied to the fluid, but half of the container is gas, right? And gases can easily compress and make room. So the force transmitted to the the pressure transmitted to the roof of this container is not going to be that high, just because of the presence of gas. It's not completely filled with fluid, and gases can easily compress. And so in this case, it's unlikely that the roof of the container will fly off. So please feel free to pause the video and make sure that this is clear to you. And then let's look at a demonstration of this. It's probably best if you watch this on your own computer so you can hear his commentary. All right, so now he's going to fire the bullet, and this is what I was talking about. You can see the action replay over here. So the container that was completely filled with fluid has its lid, the roof completely blown up, and you have a jet of fluid rushing out from the top of the container. The one that's not completely filled with fluid does not have its roof blown away. All right. There's another interesting application of Pascal's principle, and that is the hydraulic lift. So you might have seen that in many mechanics shops, they have these platforms in which you can put a car, and the car is easily raised up. Right? No matter how heavy the car or the truck is, the platform has no problem lifting it up so that the technicians can work underneath it. So how do these how does such a platform work? So this is called the hydraulic lift, and one way of doing it is to use Pascal's principle. So let me just quickly explain this. So the way a hydraulic lift works is the following. So you have these two cylinders with pistons, and they're completely filled with some hydraulic fluid. Okay, let's say that this area on the left is A1, and the area of the piston on the right side is A2, and A2 is very large compared to A1. So you can make it as large as you want. It could be 1,000 times as large as A1, or 100,000 times as large as A1. So that's up to you, how you construct it. So you can have a car sitting on this on the piston on the right side. Right? Okay, now suppose you push down with a force Fi. I'm just calling this the input side and this the output side, just for convenience. So I should probably call this Ai and A out, AO. Okay. So suppose you're applying a force Fi, that's the force that you're applying on the piston on the left side. We're just calling that Fi, you're pushing down. What is the pressure that you're applying to the fluid by applying the force Fi? So let's call that pressure, which is felt by point of the fluid over here, say, let's call that Pi, right? So Pi by definition is going to be input force divided by input area, right? That's going to be the pressure. Now the oil or the hydraulic fluid completely fills the space here, right? So the fluid completely fills up the space. There's no air bubbles, nothing. So this is an enclosed fluid. According to Pascal, when you apply pressure at one point in an enclosed fluid, the pressure is transmitted to undiminished to every point in the fluid, right? So that means a point over here just underneath the output piston is going to feel exactly the same pressure, right? So PO, the pressure at the output side, would be exactly equal to PI as a result of Pascal, right? Okay, what is the force going to be on the output side? So what force is acting on the output side? You know the pressure on the output side, and you know the area on the output side, which is AO. So the force on the output side is going to be PO multiplied by AO. And PO is just equal to PI. And PI we calculated was FI divided by AI times AO. So this is the crucial equation. The force on the output side is equal to the force on the input side multiplied by the ratio of the output area to the input area. Now I told you that you can make the output area as large as you like in comparison to the input area. So let's say that the output area is 100,000 times as large as the input area, right? That would mean the force on the output side is 100,000 times the force on the input side. So you would just have to apply a moderate force on the input side, and you would get a huge force on the output side, which would be enough to lift up a vehicle. So this is the principle of the hydraulic lift, and it is an application of Pascal's principle. Okay. In the next slide, I have a numerical example based on this idea. It's basically plug and chug. So you can work this out on your own.